Okay, good morning. Yeah. All right, and welcome back. So yeah, I posted a little message there. Something happened to the video from Monday's class. So if you tried to find it on YouTube, which they're usually there after class, the video got it was only like a few seconds. It didn't get completed, and so I think I messed something up. So sorry about that. And if you need help on Monday's exercise, if you missed the class and you couldn't complete it, please let me know. But yeah, I can't. I didn't get the video finalized for that class, so I can't put it on YouTube. But shouldn't happen again. Looks like we're good to go here. So hopefully I don't mess it up again. Okay. All right. So today we're gonna do example 5556 in chapter 5 in your textbook. Okay. So there's two exercises, but they're pretty short. And I think we'll have plenty of time to complete them. And then yeah. So if you go ahead and go to example 55 and 56, on Blackboard, you can open up the Word document. Okay, so we're going to do a couple network models on the shortest path um, kind of type of model. And so there's a little video you can look at that if you want, but we're basically trying to model, it doesn't necessarily have to be distance, like path meaning distance or time to travel that distance. The first one is distance, and the second example, 5, 6, is using the shortest path theory or type of modeling to do a shortest path for something that's not actual distance, but you can use the shortest path technique for a lot of things. Okay, so let me read the description for example 5.5. And 5.5 is really short, but it's kind of a nice summary of what the basics of doing a shortest path technique. All right, so this is example 5.5, which is the shortest walk across the state. So Maud Jenkins, a 90-year-old woman, is planning to walk across the state west to east to gain support for a political cause that she favors. She wants to travel the shortest distance to get from City 1 to City 10 using the arcs or the roads shown in figure 5.25. The numbers on the arcs are miles. Arcs with double-headed arrows indicate that travel is possible in both directions with the same distance in both directions. So what route should Maud take? So we're trying to minimize her walking path from node 1 to node 10. So these are all different cities. You can see that she can't just walk directly because she's got to, stay in a hotel, or she can't do it all in one day. So the point is for this exercise is to literally find the shortest path from here to here. So we can use these routes, and you can see that some you can go from like 3 to 4, but just like last time with network models, if the arrow only goes one direction, you can only go that direction where the arrow is pointing. So we're going to find the shortest path, and these are the miles. So this is like 63 miles from City 1 to City 3. So let's see if we can get her there the fastest, or not the fastest, but the shortest path solution. Okay, so if you open up the shortest path Excel document, that's for the exercise 5.5, which we're about to do. Okay, open up this one first. Okay, so it's pretty simple what we're trying to do here. So you can see that these are all the options, like going from City 1 to City 2, and that's the corresponding difference. And like all network models, here there's only one person, so if we choose it, she does the route. Um, If we don't choose it, she doesn't. So we're going to get the sum of all the distances between the cities she chooses to walk to and from. And then the total, which we're going to minimize, is the total distance to get her from city 1 to city 10. Okay? And yeah, that's really the whole gist of this model. It's pretty simple, and it's not a really realistic situation, but it gets you the idea of what the shortest path technique does. So, okay, example 5.5. We've got the shortest path, and so let's set up the model with the color coding and make a few range names. All right, that's step 1, or that's the pre-step. Okay, the distance is, these are all inputs because the distance between the cities isn't going to change, right? So this whole area, under distance C5 to C39, that's blue for inputs. Okay, that's our only input, and we're choosing like all of we always choose the flow in network models. So this whole area in the corresponding D column, D5 to D39, you can color that light red for the decision variable range. Okay, and let's put numbers in there for now. Let's put zeros in there for now, and then once we run the solver, if she chooses to walk the route, it'll put a 1 in there to give her that distance. If not, it'll remain a 0. So for now, just put zeros in the D flow column here. Okay, so we got zeros in D5 to D4 to D5 to D39. Okay, and then the objective is just total distance. So we're going to minimize cell B42. That's the highlight yellow color for the objective. Oops. Okay, and we have one constraint, which is the flow balance constraint for a shortest path model. And we'll do this in a little bit, but all the net outflows have to equal the required net outflow. So just put an equal sign. There's no inequality. It's just this has to equal this at every step. So put an equal starting in H5. And you can either type it in or kind of grab the bottom right corner, but you want an equal sign in H5 to H14. Okay, so this is our constraint where all of these cells have to be equal to these cells. And so put an equal sign in H5 to H14. Okay, so if just if it looked like some people just joined because when I started there was only like 4 students. So we're doing example 5556, and the file we're using right now is the shortest path. So example 5556 and shortest path. Okay. Oops. Okay, so let's make some range names, and then we'll go ahead and start solving this. So we got this is our these are our inputs. This is the decision variable range. This is the objective to minimize total distance, and this is the only constraint where net outflow has to equal the required net outflow for each node. All right, so we got that set up. And because of the simplicity of this, we're basically going to make a range name for everything you see. Um, and I think the easiest thing to do is just make these 4 range names as all at the same time if you want to select origin, destination, distance, and flow. Okay, A4 to D39, just select that whole region. And let's go ahead and do formulas, create from selection. Top row, Okay, and that's going to make a range name for origin, destination, distance, and flow. Let's make a range name for total distance, which is the objective. Okay, so select A42 and B42. Formulas create from selection left column. Okay, and then let's also do, what is this? Net outflow. Okay, so select G4 to G14. Formulas create from selection top row. Okay, and then required net outflow. I4 to I14. Formulas create from selection top row. Okay. And so let's see if you click on the name manager, just double check that you got these range names. So we got destination, distance, flow, net outflow, origin, required net outflow, and total distance. So we basically named everything, but just go ahead and double check and make sure you have these 7 range names set up there. Okay. All right, so everyone good so far?
Did you make one for all three of them combined? So origin, destination, and distance. You made one for all of them combined.
Yeah. If you just select all of them together and do the process with the formulas create from selection, it'll do them all together.
Mhm.
Yeah, so that's the shortcut just to do if you do them all, it'll do all the adjacent ones.
Oh, that was if you want to do them all at one time.
Yeah, so you can do them individually, but probably the best way is Excel knows
Yeah,
what you're trying to do. So select them all like that, and your formulas create from selection and top row. And Excel knows that this will be the name for that, this will be the name for that, and this will be the name.
yeah.
So
Okay,
if you
for
select
sure.
them all at once, it'll save you some time there.
Yeah, I got you. Actually.
Okay, so these are the ones you should have. Again, these 4 together: origin, destination, distance, flow, and then the objective is total distance. And you got these ones over here: net outflow and required net outflow. So that's all you need here. Okay, we are going to do, well, step 1 is to set up the arc list, which is already done. So if you were starting again, a network model from scratch, the first thing you absolutely want to do is list all of your possible arcs or connections, and those are listed here. So if we had to set this up for a different problem, we'd first put the origin, the destination, the distance column, and put all of the possible um, options here. So going from 1 to 2, 1 to 3, based on that diagram. Okay, this one. Make this. There we go. Yeah, this one here. Okay, and remember, so last time we did a network model, but it was something a little bit different. We were trying to minimize total cost of shipping some tomato product stuff, but the idea is the same. So last time we had origin, destination, and total cost and flow. Okay, so the only difference for any network model is you're going to change this column, but you're going to specify the model as origin column first, then destination, and then here's going to be your minimizing thing, and this is going to be flow. So always set these models up with origin, destination, flow, which you're going to choose, and then this is like total cost, distance, whatever you're trying to maximize or minimize. Okay, so you can see kind of the network models. The nice thing is you can see kind of the uh, transparency of how they're all pretty similar, and once you get the idea, they're very you don't have a lot of. I think they're a lot more simple than the previous ones where you had all these different columns and inputs. Okay, step 2. net outflows, let's put this formula, if you got the range names, into G5. Okay, put G5, there's G5, and then let's put that formula equals. Okay, sum if, so make sure it's sum if, not sum if, and then the range is origin. All right, so here's your formula. Equals sum if, and then the arguments are origin, F5 flow, minus sum if, and then the arguments are destination, F5 flow. So see what we're doing is we only have one person. We have to count for her to be somewhere. All right, so she either has to, I mean, if she comes out of the origin, she has to go into some destination. She can't just be in limbo when this model is solved. And so this one person has to be somewhere when we solve the model. So see how it's what comes out of node one minus what goes into node one. If that, I don't see, she's probably not going to go back to node one, but it sets up the logic. Okay, so see how the indicator is node 1, and we're going to do the same thing for all the nodes 1 through 10 to make sure we account for where this person is. Okay, so for now you should get 0, and all you want to do is, if you got this formula, you can click on G5, double click the bottom right corner like that, and that should do the same formula. The only difference is the only change. If you go down is the F indicator, see? F6, F7, F8, and the last one, double check, should be F14, which corresponds to node 10. So you always want to double check that your F indicator is on the respective node that it's adjacent to. But same formula. So what goes um, out of the origin minus what goes into the destination. All right, and then okay, we did that. In the column in the right side of the constraint, let's just to solve this, you got to put a 1 in node 1, a 0 in nodes 2 through 9, and then a -1 in node 10 to make sure we account for the fact that she has to be somewhere, and the flows have to be 0 once it's solved. So just do this. Okay, in I5 put a 1. In all the middle nodes 2 through 9 put a 0. And then for node 10 put a -1. Okay, so just type those in, 1, and then in between a bunch of zeros, and then a -1. All right, so see how this is going to sum to 0, and this is going to mean that she's not, you know, after the model is solved, she's going to be in some destination. She's not going to be flowing, if you will. So we have to account for the fact that she has to, first of all, not be in two places at once, and second of all, she has to be at some destination after the model is solved. Basically, she has to be at node 10, right? This says she starts at node 1 and ends at node 10. Okay. Okay, step 3. Let's total distance. Let's put this formula for the objective that we're going to minimize right in the yellow cell B42. Okay, step 3 equals, and so B42 equals, okay, sum product. So make sure this one's sum product. The previous one was sum if, but this is sum product. Okay, that's it. Equals sum product distance flow, which means that if she walks on the route, if she chooses if there's a 1 here, that means she did the walk. So we add the distance, and all the flows she chooses, we add the distance together, and then the total distance is the sum of all the routes. Okay, now the next step is just to run the solver and minimize the distance. Okay, and let's go ahead and do that. Okay, so data solver. Okay, so you can kind of see what we're doing. The objective, hit the button, is total distance, B42. Make sure this is minimized, right? We want to walk the shortest distance, not the most, right? She doesn't want to wear herself out. She wants to walk the least amount possible. Okay, remember for network models, we're always going to title the decision variable range flow. So the easiest thing to do is just type it in if you made the range name. Okay, by changing variable cells flow to coordinate with that. And then we have one constraint. If we click on the add button, which is this one, right? So cell reference G5 to G14 for net outflow. Choose that. And this has got to be equal to. So you're just setting it up to look just like this here. Constraint, hit the button, is I5 to I14 for required net outflow. So see, it's just G5 to G14 equals I5 to I14, which is exactly what we have specified here in the flow balance constraint. Okay. And make sure if the solving method should be simplex LP, and this is what you should look like here. So the objective is total distance. Make sure this is minimized. Okay. Uh, Changing variable cells is flow, assuming you have the range name. One constraint, net outflow equals required net outflow. That should be checked, and this is simplex. Let's solve this. To get a solution, hit OK, and looks like we should get total distance of 198. Is that what we got?
Yep.
Okay. All right. So it's pretty simple what happened here. So we chose, or she chose, the shortest distance which was to walk from city 1 to city 4, and that was 56 miles, right? And then she walked from city 4 to city 6, which was another 45 miles. And finally, she walked from city 6 to city 10, which was 97 miles. So that was the shortest option that Excel found. And so that's what she would do, is walk from 1 to 4, 4 to 6, and then 6 to 10, and then she's there. So the total distance, which is essentially just 56 plus 45 plus 97, right? Like pretty rough last day, 97 miles, 198 total. Okay, and see how the way we set up the flow balance constraints is confirmed. So this is 1, these are zeros, and then this is -1. You add all this together, that's 0 to account for the fact that she's in the destination and not out there in limbo on one of the flows. Okay. All right, so that's example 5.5, I believe, is done. So you can save this one. Everyone's got this one done, yeah? You can save this one and close it, and then that goes here by next Monday. But we have another one to do. So we did example 5.5. Now let's do example 5.6. So you're going to have two Excel files, and you can either I, I don't believe you can post two Excel files at once. So you can either make two posts, or I know you can post one Excel file and then reply to it. So that's often what students do is post one of them and then reply to it with the other one. So that way it'll be in the same post. But if you make two posts, that's fine. Okay. This- Okay, we're done with this one. Now let's do a shortest distance or process to a different problem, which is example 5.6. And let me see if I can find the description here. But you want to open up the machine replacement Excel file. Okay, this one. All right, go to example 5556. Shortest path is done. And let's now do example 5.6, which corresponds to machine replacement. Okay, so you can see this is a much more uh, complicated model, but we're going to use the same idea, all right, which is basically use the shortest distance method to do a different problem. All right, so let me read this one. Example 5.6, which is equipment replacement at Van Buren Metals. So Van Buren Metals is a manufacturing company that uses many large machines to work on metals. These machines require maintenance because of wear and tear, and it's sometimes advantageous from a cost standpoint to replace machines rather than continue to maintain them. So this is just like, if you have a car for 10 years or 15 years and something goes wrong and you go to the dealership or not the dealership, but the service center, and at some point the cost to fix it is going to be more than the value of the car. So at that point, a lot of times what you want to do is not pay the expensive cost when you have an old car, but instead probably looking to getting a new one or a used one because at some point the cost to maintain gets too costly for what it's worth. So same idea. For this type of machines, we got the quarterly cost of maintenance, the salvage value, you can resell it, kind of recycle it, the cost to produce a new machine, and these costs depend on the age of the machine. So the longer it goes on, the less it's worth, and probably more likely the more it costs to fix it. Okay, but we simplify here to have no inflation to make it simple. But if you're doing this in a real world situation, all you'd have to do is kind of put the values in real terms. So if you don't want to if you don't have it if you have like the prices specific for that year, you could easily convert them to 1 year's prices, and that way you control for inflation. We're not going to do that. This is not a um, macroeconomics course, but if you did this, you would want to do some kind of control for inflation. Um, Purchase cost is 3,530, and it's $100 to maintain the machine the first quarter, and then each consecutive quarter it's an additional 65. So obviously it gets more expensive to maintain it. The longer it goes on, the more wear and tear it has. There's more things that can go wrong. And the salvage value after one quarter is 1530. So you can see that just like a car, the value really drops right away. I mean, it's like cut in half after one quarter. And then after each quarter, the value drops by another 110. So we want to decide how long we should use the machines and when we should start to replace them. So what should we do there? They do have a company policy that they never sell a machine that's less than 1 year old, and they never keep it more than 3 years. So we're going to find some sweet spot in between, and also the machine in use at the beginning of the quarter is brand new. So what we want to find here is what's their best um, machine replacement strategy. So how long do they use it, and when's the best time? When's like the marginal time to get a new one, right? When does it become more costly to maintain it than to buy the new one? Well, we'll find out. Okay, machine replacement. Okay, so we got all the costs up here, and the network model is set up in which these aren't distances, but they're like time distances. So this is quarter one to quarter five, which means you keep it for 4 quarters. And this is the specific maintenance costs in each of the 12 quarters, right? The most you can have a machine is 3 years, which is 12 quarters. Okay, and we need to calculate all the costs and choose the minimum cost situation. All right, we have a bunch of columns here, but it'll go quick because we're going to write a formula that applies to all of these quarters. Okay, okay. So first thing we'll create uh, range names. Well, let's do the color coding and do the range names for these things, and then we'll start uh, doing the calculations. Okay, these are all inputs that say inputs up here, so you can color these numbers light blue for inputs. Uh, okay, those are the only inputs. The flow area is, again, the objective cell, so you can highlight this whole area. Okay, it's a big area, but it looks like it's S14 to S130, S14 to S130. So this whole area, just make that light red that's going to be our decision variable range because we always choose the flow. Okay. Um, total cost is our objective to minimize. So cell V36 is yellow or highlight yellow for the objective. Okay, and then our only constraint for the shortest distance type of models is the flow balance constraint, which means the net outflow has to equal the required. So just put equals uh, right here in this column. Okay, there you go. So there's our constraint with the equal signs. Our total cost to minimize, we're going to choose which flows we want to choose. And then these are the inputs up here. Okay, so range names. Next, let's make range names for, let's see, origin, destination. So it's a big range. Okay, so select A13 all the way to B130. A13 to B130. And then formulas, create from selection, top row, okay, and that'll name this origin and this range destination. Okay, we need a range name for, we don't need a range name for these things in between, but we need a range name for total cost and flow. So you can select this range. Okay, actually, um, we have two total costs here. So I think the total cost we want to name is this one. Yeah. Yeah, okay. So don't name this one because we have two total costs, right? So it has the same name. We can only name one, or unless we do different names, but we need to name this one, so leave that one. But we got to name the flow. Okay, so select the whole flow column. Okay, so select S13 to S130 and formulas create from selection top row. Okay, so that's called flow. And then we have three more, I believe this one, and this one. Yeah. So V13 to V34, make a range name for that. For required X13 to X34, make a range name for that. And then for total cost. So just the objective, which is selecting U36 to V36, and then formulas create from selection left column. Okay. So let me click on under formulas the name manager. We got destination, flow, net outflow, origin required and total costs. Okay, so double check that you have those six range names there in the name manager. Okay, and remember they're big ranges, so make sure that the main range was 14 to 130. So see how these are all 14 to 130, 14 to 130, 14 to 130, and so make sure that your destination and your flow and your origin get the correct range there, or the whole range. It's a big range. Okay. Okay, we did the range names and the inputs are already done and the arcs are already done. All right, so let's just note what that. All right, so okay, the inputs are already set up. And again, if you were doing this type of model, you'd first put your origin and your destination and all the options, like quarter one to quarter five, quarter one to quarter six. And this, the quarters to keep, just calculates the difference. So if you keep it from one to five, you keep it for four quarters. If you keep it from one to six, you keep it for five quarters, right? So these are the arcs, and this is how long you kept it because we need to know how long you kept it to get the total cost. All right, so this is done as well. That means we're on step 4. Okay, so we're going to put the maintenance cost, which is this big formula, in D14. We're going to copy it to this big range. All right, so this is the bulk of the exercise here. Okay, in D14, which is right here, put in that formula you see in step 4 equals. Okay, if Oops. All right, let's double check this formula. We'll go through it a couple times. So the formula is equals if, and then in parentheses D, $13 greater than $C14, comma 0, comma $B, $6 plus $B, $7 times parentheses D, $13 minus 1, and then double parentheses. Okay, so put that one there and let me explain what it means. All right, so we're trying to calculate the maintenance cost in the specific quarter. So this tells us if so this is quarter one, and it tells us if that's bigger than if that's bigger than 4, which is not, then this is the way you calculate it. Okay, so it's telling us that if we just bought the machine, this is the cost. If we didn't just buy the machine, then we have to add it by doing the 65 plus every quarter. So here, D13 is bigger than C14. That's not the case. So that's a 0. But then do this. It's 100 plus, so see how it's not a new machine. Okay, so it's not just 100. But now, quarter one is bigger than that. So what we do is we add 100 plus 65 every additional quarter, which is what this does. So what this does is it tells you if you're in the um, let's see. Oh, no. Okay. So this tells you if this is less than this, that means you're not calculating the costs. But if it is, you do this. So basically, it's 100 plus 65 every quarter. So here we kept it 4 quarters. So that's going to be 100 plus 65 plus 65 plus 65, right? Okay, so there's the 100 in the first quarter. And if I were to drag this over, it would give us another 65. And then when you get rid of it, um, that's when it goes back to 0. So all of these arcs coordinate with keeping the specific machine for that given time period. All right, so if you drag this over like that, see, if you keep it for 2 quarters, it's 100 plus 65. All right, and then if you keep it another quarter, it's another 65. Okay, so double check this formula. Equals if D $13 greater than $C14, comma 0, comma $B6 plus $B7 times parentheses D $13 minus 1, double parentheses. Okay, so you got to have that exact formula because it's going to apply to this whole big range. Okay, if you got that formula, grab the bottom right corner and drag it over to 12 like that. Okay. And actually, leave it there. We'll copy it down in a minute. All right, so see what's going on here. This is the only option we're looking at is this one, which is keeping the machine from 1 to 5, which is 4 quarters. Okay, so if you keep it from 4 quarters, this is our cost structure, right? In the first quarter, it's 100, then another 65, another 65, another 65. Now, it's 0 from here on out because if we only keep it for 4 quarters, then we don't pay for it anymore. So we pay for a different machine. So these are the 4 quarters. And then in quarter 5, we get rid of it. So the cost from there on out for the rest of the model is 0. Okay? So that's the idea. Okay? If we keep it 4 quarters, we pay the cost every 4 quarters, and then after 4 quarters, it's gone, it's 0. But this depends on how long we keep it. Okay, here we're going to have another 65 because we kept it for 5 quarters. Okay, so select D14 to O14, all right, all of this. And then you can just double click the bottom right corner, and that's going to apply this formula to all of these options. So just do this. Okay, and it should, and if these come out like dollar signs, that just means that you got to make the cell bigger. Okay, so that should have done the maintenance cost for every specific option. See? Where you pay, the longer you keep it, the longer you have to calculate the cost, but you can see once the zeros start right when you salvage the machine. Okay, so you should have a maintenance cost calculated for all of these cells here. Up to O130. Okay, so everyone got this?
Yes.
Okay. All right, so we put that formula in and we copied it from D14 to O130, which calculate all the options that we can choose in keeping this machine. Okay, salvage values. All right, so the only thing we've done so far is the maintenance cost, but there's additional cost, or there's a salvage value is like a credit, right? So if we retire it, we get some value for selling it back, but then we have a purchase cost. Okay, so in step 5, put this formula in P14. All right, so P14 equals equals $B, $9 minus $B, $10 times parentheses C14 minus 1. Okay, so the salvage value gives us the appropriate salvage value. So if we salvage it after 1 quarter, we get this. And then each additional quarter we keep it, we subtract 1/10. All right, so this one, we kept it for 4 quarters, which means that it's going to be 1530 minus 110 minus 110. Okay, which is like, uh, should be what, 1,310? 12, I don't know, that was not the right math. Okay, so see how it looks at, it takes we keep it for 4 quarters, right? And so that means that we get 4 minus 1, which is 3, and that's going to be this minus this times 3. So this is for the initial, and this is for the additional quarter. So it's 1530 minus 110 minus 110 minus 110. Okay? There we go, 1200. All right, then if you got this formula here, you can double click the bottom right corner and apply it down for all the salvage values like this.
Can you show that formula one more time, please?
Yeah, this one. Okay,
Yeah.
it's equals $B, $9 minus $B, $10 times parentheses C14 minus 1, close parentheses. So it's specific. It's calculating the specific salvage value given the number of quarters you keep it. So it's always 1530 plus 1 minus how many quarters you kept it.
Okay, cool. I got it now. Thanks, man.
Yep. All right, so see how it works. if you go to the second one, or let's just double check the last one to make sure we got them all. Okay, so this one, see, we kept it, well, it's the same as the initial one, but we kept it for 4 quarters. Let's do a different one. How about this one? This one, we kept it for 9 quarters. So the cost is the initial salvage value, and then each 8 quarters we keep it after that, it loses the value of 110. So it's basically 9 quarters. This is the salvage value to start with, and then you subtract this 110 each consecutive 8 years. So it's 1530 minus 8 times 110, right? Which is that? Okay. Okay, the purchase cost is easy to calculate. Just put, well, equals that. Equals $B $4 in O14, because it's always the same. Not O14, Q14. Q14 is right here, so the purchase cost is equals $B $4. So the purchase cost is always $3,530 if we buy the new machine. Okay, and just double click the bottom right corner and apply that 3530 down, like that. Okay. Total cost, step 7. So we're going to put the sum formula to get the sum of the total cost in R14, which incorporates the maintenance cost, the salvage value, and the purchase cost. So it's basically maintenance cost plus purchase cost minus the salvage value. This is like a credit. Okay, so let's put this formula in R14 right here, equals I don't know what happened. Okay, sorry, equals sum D14 to O14. All right, I think that's it. Let's see. Yeah. So the formula is equals sum, and then in parentheses D14 to O14. Okay, close the parenthesis, then minus P14 plus Q14. Okay, so see what we're doing here. The total cost is the sum of all the maintenance costs. All right, minus the salvage value, we get that back, and then plus the purchase cost. So there's 3 components. Okay, we got to pay for this, we got to pay for this, and we get a refund for this. So this minus that plus this is the total cost, right? Okay. Then just apply that down. So total cost, click on R14, double click the bottom right corner. There we go. So that should give you the total cost for all of the options here. Yeah. Okay, step 8 is just we gotta put some values into the flow column. All right, and so that way, if we choose it, it's 1. If we don't choose it, it's 0. Okay. All right, so just put zeros in here for now in the flow column. All right, so the easiest way is just put a 0 in F14 and then double click the bottom right corner and that'll put a 0 in the whole column like this. All right, so you got to have zeros in there or values in there. Okay, so we got the maintenance costs in each of the 12 quarters, the salvage value, the purchase cost, the total cost, and the flow for all of these options. Yeah. Okay, and then we're going to set it up just like we did the rest of the shortest path in the across the state one. So all we have to do next is set up the net outflows and then calculate the total cost and then run the solver. All right. So let's first do let's do the right side of the constraint first. So this will be the same as before. So basically, for all of these shortest distances ones, put a 1 in the first node. Okay, under required in X14, and then put zeros in between. And then put a -1 in the last one. So in X14, it's 1. In all of these ones, X15 to X32, it's 0. And then the last one, in X34, it's -1. So 1, a bunch of zeros, and then -1. Okay, and then in V14, let's calculate the net outflow, which is equals okay, sum if, make sure it's the sum if one. Okay, origin, comma, what is this indicator here? U14, comma flow. Okay, so here, let me run through this one again. So it is equals sum if, and the arguments are origin, U14 flow, minus sum if, and the arguments are destination, U14 flow. Okay, so make sure you have your range name set up for origin and flow, and then the U14 is just indicating the node. So it's going to say what comes out of node 1 minus what goes into node 1. Okay, so double check that your range names are highlighted to indicate that you set them up. So origin flow are range names, and then U14 is just this node 1 here. All right, and then we can just apply that down. So click on V14, double click the bottom right corner like that, and that should do the formula all the way down to node 21. So see how this one is the same formula, but the U34 indicates that we're looking at node 21. Okay, and then total cost is just in, what are we at? V36 in our objective yellow cell equals sum product, total cost, comma flow. Oh, we didn't do that total cost, did we?
I don't think we did, Professor.
Yeah, because I actually I wanted to do this one instead of that one. But I did the wrong one. Okay. Well, let's just select it. Okay, so let's do sum product. And then choose the whole range, I guess. Sum product, which is R14 to R130. All right, so just select this whole range, all the total cost there, or type it in. So sum product R14 to R130, and then comma, flow. All right, so that should do it. I mislabeled the wrong range name, but it doesn't make that big of a difference. So this is total cost, but we didn't name it, so it's equals sum product R14 colon R130 comma flow. All right, so if you do that, it should work fine. And right now it's 0 because we don't have any flows.
Hey, Professor, will it matter when we're doing the solver though? When we do the range names?
No, we're just gonna have to select it.
All right.
Actually, we don't actually won't matter at all because it's part of this calculation. So as long as we're choosing the flow, and this is the objective, and we have no, it's not going to matter because it's not something that's specified implicitly in the solver. And
Okay.
the only thing that made a difference is that if you were looking at the printout, I put in distance here, and we didn't label that distance, but it doesn't.
Got you. Okay.
Yeah. Okay. So just yeah, as long as it says equals sum product, and then R14 to R130 comma flow, that should work. And this range, the blue range, is what we should have called total cost, but I labeled the wrong total cost. All right. Everybody,
Professor,
yeah,
could I see the net outflow like equation again?
this one?
Yeah.
Yeah, so it's equals, make sure it's sum if, origin U14 flow minus sum if, destination U14 flow for the first one. And then when you copy it down, it should be like this is U15, U16, all the way to U, whatever this one is. Okay, did you get it?
I'm having problems. Like it says that like I have like too few like parentheses or something. Like I can't.
Uh, um,
Yeah.
yeah, so make sure the only parentheses are these ones for the first sum if, and then make sure you close it there. All right, so you have the first sum if with the parentheses and then minus the second sum if with the other parentheses. So see how there's just sum if and then minus. Make sure you got your parentheses there. Okay, and then after that minus, then you got your parentheses there.
Oh, okay. Thank you.
And then make sure you apply it down to all the other ones, and you can double check your last one to be this one, which is equals sum if origin U34 flow minus sum if destination U34 flow.
Okay, got it. Thank you.
Yeah. All right, so everyone else good before we do run the solver? Okay, so we're going to tell solver to choose the lowest cost options and minimize total cost based on how we set it up. So let's go ahead. And so we're using the same logic that we did in the walk across the state to find the shortest distance, but in this case, shortest distance is actually lowest cost. Data, solver, objective, click on this button is total cost, the other total cost, which is V36. Okay, actually, it'll show up as total cost because this is the one we labeled, but objective is B36. Minimize that, right? Minimum, you want to pay the least amount. We're changing flow always. And we have the one constraint, which is that net outflow equals required. So subject to the constraints add, cell reference is V14 to V34 for net outflow. Make sure this is equals, just like we show in the spreadsheet, and the constraint is X14 to X34. Okay, so V14 to V34 equals X14 to X34, okay? And I don't know why this is always the wrong thing, but this should be simplex LP. Okay, here we go. So objective total cost, right? This total cost, or or just make sure if you didn't label it, it should be V35. No, V36. So objective is V36 or total cost if you made the range name. We're minimizing that. We're changing the flow, and net outflow equals required. This is checked, and this is simplex. And I think that's it. We can solve it. Did we get a solution? Okay. And I think that's right. 13,575. Is that what we got?
Yep.
Okay. That's what we should have gotten, I believe. So let me know if you did not get that, and I'll help you. But this is basically for one machine. For each individual machine, this is the best case scenario. So given the options we have, we should keep it. Let's see. So there's a 1 here, which means that we chose to keep it from quarter 1 to quarter 7. All right, so we're trying to find the best strategy to get this to have a machine operating from quarter 1 to quarter 21. All right, we can't keep it longer than that, but we can keep it less than that. So what we chose to do, the lowest cost scenario is to keep it from quarter 1 to quarter 7, which is keeping it for 6 quarters. And we pay this amount. And then after quarter 7, we keep it from quarter 7 to, so basically we keep it for 7 quarters. All right, so we keep it for the first 7 quarters and pay 41.25. We keep it for another 7 quarters and pay 47.25 because we had to buy the new machine, and then we keep it for 7 more quarters. Okay, so we were trying to find the best case scenario to have a machine that could be kept up to 21 quarters, right? But we found the low cost or the best situation is to keep it for 7 quarters and then get rid of it and get a new one, because at that point after 7 quarters, it must be that the maintenance cost is too high. So we found that the point when this machine gets too costly to keep maintaining, which here is keep it for 7 quarters and then replace it after every 7 quarters. So that's what you would tell your management, all right? The low cost scenario for this type of machine is replace it every 7 quarters. Okay? And that gives us a total cost per machine. The best case scenario is 13,575. Yeah, okay. Okay, so if everyone's got this one done, I think we're done with this one. Okay, so if you got this, you can save it, and you can post it in the same area. Right. Okay, so for example, 55 and 56, you want to first post the the shortest path Excel file. And then you also, like I said, you can only post one file per thread. And so either, I think the easiest way is just to post once and then reply to your post and post the other one, right? Because you want to post both the shortest path and the machine replacement, the one for both 5.5 and 5.6. And so either reply and post each one individually or make two posts. Okay, so I don't know if we've had to post two things at the same time, but that's how you would do it. So I think, like, Tyler, if you would to just, oh, you've already done it. Okay, yeah. So do what Tyler did. Post your first one, shortest path, then reply to it, and post the other one. Yeah. Okay, so we're just about done with this exercise. So let's see. For Monday, if you haven't turned them in already, you've got example 5.4 and example 5.556. So these two are due Monday if you haven't done so. And like I said, I made a little note that sorry, but I messed up the video for Monday. So the video for example 5.4 is it didn't get finished, so I don't have a video for that. So I can't post it to YouTube, and I apologize. But if you need help, or if you need me to set up like an additional meeting, I can do that. So if you have any problems with example 5.4, if you weren't here Monday, please let me know or send me an email because I don't have the video to put up for that one. But I have this one and I have all the other ones. So I just something happened to this one. Okay. And I think that's it. So that's what I want to do for this morning. Uh, everyone have a good weekend, and I'll see you on Monday, and we'll do example 5.7. So thank you for joining, and have a good weekend.
See you, Professor.
Thank you.
Wait, Professor, I have a question.
Yeah,
Can you show me your solver
sure.
for the last exercise?
Okay, there you go. Can you see that?
Yeah, I have that exact same thing, but I'm not getting a total. I'm just not getting one at all.
Okay, well, can you post it and I'll look at it?
Yeah. Okay, I posted it under my replied comment from earlier.
Okay, this is Ryan, right?
Yes.
Okay, yeah, this one.
Yeah.
Ooh, I think it's probably just I think you chose the wrong cell for the objective. It looks like it should be V36. And I think that and this needs to be changed to simplex. So I think everything that should work. So let's try it. So just change your objective to V36 and change the solving method to simplex LP and try to hit solve. And yeah, and that does it. Did that work?
Yeah, it works. Thank you.
Let's see, did it work? Yeah. All right, perfect. Okay, so you're good on that one, yeah?
Yeah. Thank you.
You're welcome.
Have a good weekend.
Okay, you too.